Alright, good evening everyone, my name is Dolphin Malaban, and today I'm going to give you a short video review on what to do in order to solve the quiz problem given in class. So let me read out the problem. A block of mass m slides down a frictionless ramp that is 37 degrees up from the horizontal, starting at a height of h. Once at the bottom of the ramp, the block moves onto a horizontal rough surface with a coefficient of mu and slides over displacement x. Derive an expression for mu using only kinematics and dynamics and not including energy. So let's draw a quick picture, right? You have a ramp, pardon my art. We have this distance, which is going to be represented by x. We have h. We have this block over here. And I'm just going to draw the block as it's done. You have the angle here, which is 37 degrees. And yeah. So in order to solve this problem, first what we need to know is that we need to know the speed at the bottom of the ramp. This is because once we know the speed of the bottom of the ramp, then we're able to do some manipulation using some kinematic equations in order to be able to find mu. So let's do that first. So the key equation that we need in order to solve this problem is vf squared is equal to the initial squared plus 2ad. We will need this equation twice. Okay, so we know at the top of the ramp that the velocity is 0, right? As it's not moving when we drop the block initially, right? So we could assume that this is 0. However, the acceleration of the object and the distance that it traveled of the object is something that we do not know, which is something that we'll solve for. So let's solve for distance first, right? If we assume that the overall slanted length of the board is considered by this length L, or in this case, let me erase that to make it a little bit more concise. We'll say D in this case, right? Because this is the actual total distance that it's sliding. We can derive using simple trigonometry, using SOHCAHTOA, that sine 37 degrees is equal to opposite over hypotenuse. So carrying stuff over by multiplying this across and dividing the sine 37 degrees on both sides, we are able to get D is equal to h over sine 37 degrees. And through drawing on the force diagram, right, as it goes down, as this block goes down, it can be represented by mg sine theta, as it's on its slant, as this is on the slant. Yet the block is sliding down on the slant, therefore it can be represented by mg sine theta. Sorry for being redundant. So once we have that, we're able to find the velocity as it hits the bottom. So just to write that out, vf squared is equal to 0 plus 2 g sine 37 degrees, because just to clarify my explanation, the normal equation is m is equal to ma, and this is our force going down. We could assume that the acceleration is g sine theta in this case, multiplied by h over sine 37. So these actually cancel out, and we're able to get vf squared is equal to 2gh, or vf is equal to 2gh the square root of that. However, we're not done. We need to find x, right? What we can do again is that, yes, we need to find the acceleration, right? So in this case, this is our new initial, as this is when we're measuring the movement as it slides across this distance x. So we'll write the equation again. Vf squared is equal to v initial squared plus 2ad. We know that the final velocity is equal to 0, and our initial is what we just solved for, which is square root 2gh squared plus 2ad. Or in this case, it would actually be represented by x. So it might seem that we're on a standstill, right? What is a? However, we're able to represent this as we know that as we're able to find this, as we're given another clue, that there's a coefficient of mu, or there's a coefficient of friction as mu, known as mu. And we have an equation. I like calling it the fun equation because it looks like you're spelling the word fun. Lowercase f, which is the force of friction, is equal to mu multiplied by the normal force. And since the normal force in this case of the block is just going straight up and down, you don't have to account for any things, we could say that N is equal to mg. If it was on the slant, you'd have to account for the angle. However, we're not going to get into that. So we could actually expand this, right? F is equal to mu mg. However, we know also that the force is equal to ma. So in this case, if that's equal to ma is equal to mu mg. Doing some unit cancellation, we could do, your acceleration is equal to mu g. And that's actually going to help us a lot in this case. So we have everything we need now, and all we do is substitute everything in and expand. So we have 0 is equal to 2gh plus 2 mu gx. So doing some multiplication and carrying this over to the other side, we have negative 2 mu gx is equal to 2gh. Once we do that, we can cancel out some units here. In this case, the 2 and the g would both cancel out. So we have negative mu x is equal to h. And dividing both sides by negative x, we have mu is equal to negative h of x, which would be our answer. However, I also said I would be solving this via energy. Although it says not energy in the top, energy can also be used to solve this problem. And it is actually very, very short. It's much more simpler compared to this more complex method. So, as we know, gravitational energy at the top, or gravitational potential energy at the top, can be represented by, I'm just going to write this out as an initial, PE is equal to mgh, and kinetic energy, KE, is equal to 1/2 mv squared. However, when it comes to the ramp, actually, this does not matter, as we pre-established already that we established that it's frictionless, right? So no energy is being lost. Work energy theorem, or the conservation of energy, states that unless there's an external force acting, energy will always be maintained, right? It cannot be taken out of the system. So you can use kinetic energy, right? However, we're trying to find this in terms of all the variables given. We're not really given a velocity that it left at, and that would just give you more of a variable mess. So we could stick at the bottom that the potential energy, or the energy at the bottom, would be equal to mgh. However, we do know that work was done on the system. So work is represented by force times x, and we know that the overall total energy of the system is 0 as the system stopped. F in this case of the block is equal to mg. So this is actually super simple. mgh plus mgx is equal to 0. mgh is equal to mgx. Oh, no, never mind. Sorry. I forgot, I omitted a step. Well, okay, yeah. You have mgh, right? However, the force done is the force of friction. My fault. It's the force of friction. And that is basically F is equal to mu. And we established that the normal force is also equal to mg in this case. So in this case, my fault, we could just add a little mu here, add a mu here. Make this negative, and through dividing, we're able to get mu is equal to negative h over x. Sorry for the long explanation and sort of messy handwriting. However, this is my explanation on how to solve this problem.